Welcome to A Picture in 1,000 Words, brought to you by the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. In this series, we'll be breaking down some of the most iconic images from space from the perspective of an astronomer. That's me. My name is Mubdi Rahman, and I'm an astronomer at the Dunlap Institute for Astronomy and Astrophysics. And just a reminder that if you're watching live, please feel free to throw a couple questions into the live chat somewhere over there, and we'll try to get to a few at the end of the episode. So why don't we dig right in? And today we are talking about this incredible image of the remnant of supernova 1006. So the key thing to remember here is that this region and this picture, it's all about what happens when a star dies, and a couple stars die actually, and they crash into one another. So this region is in the constellation Lupus. So for the Harry Potter fans out there, this might sound familiar. This is because this is in the constellation of the Wolf. The region is about 7,000 light years away. So it's far. A light year roughly is the amount of distance between us and the closest star. It's about a light year or so. But in astronomical terms, it's actually really close. This is our neighbor. It's, only 7,000 light years away. And this region, it's about a degree on the sky. So that would be roughly the size of a full moon. And we're talking about a degree at the distance. That looks like a bit of a face, but at this distance, that is about 65 light years in size. So our solar system would be kind of just like a tiny little speck in there, right? There are many stars that this region would probably encapsulate. And the key thing about this image that's really cool is that this is not actually taken from only light that our eyes can see. This is going well beyond it. So all of this blue over here, this blue is coming from X-rays. These are X-rays that are being detected by the Chandra Space Telescope. So that's up in space, and it's orbiting around us somewhere, and it's getting these X-rays because those X-rays can't penetrate our atmosphere. The red, on the other hand, that's coming from radio telescopes. So those are massive, what look like massive satellite dishes, and they're pointing at space and they're mapping these regions. The radio telescopes that were used to take this kind of data, they are in New Mexico and West Virginia in the United States of America. But then finally, we have a bit of optical light. And so this optical light, I'm going to say it's green, but it looks yellow here, and I'll go into that in a second. These are from telescopes that are up on mountains in Chile and another one in Australia. And that's what you're seeing here. All these stars over here, that is coming from optical light. So this is the kind of light that you actually can see yourself. So we're going to colors that are much, much bluer than our eyes can see, all the way to things that are much, much redder than our eyes can see. Things that are actually more, like the signals that come into your television or into your radio set. But the key thing to remember is that this is the aftermath of a major explosion, a supernova. And what's going on here? So you're seeing basically a massive bubble. This entire thing is a bubble, and everything you're seeing is essentially the edge of a bubble. And all of the gas that's in this bubble, it is hot. It is because it's been an explosion. And what am I talking about when I call it hot? It is about 10 million degrees Celsius or 18 million degrees Fahrenheit. So it is super hot. And it's making all of this gas, everything that you're seeing here, all of that is a plasma. So it is so hot that the gas can't even hold on to its own electrons. It's all mushing up in there because there's so much energy to go around. And the other thing is it's moving outward. All of this gas is being sent in every which way, as you can imagine, because it's an explosion. It's just going in every single direction. And when this gas gets moving really fast and it's really hot, what does it do? It produces strong magnetic fields. So there are some incredibly strong magnetic fields going on here. And so all of the light that we're seeing is related to either the fact that this is really hot gas that's moving very far, or that there are a lot of strong magnetic fields. So let's talk a little bit about these magnetic fields and the light that they're producing. So all of the red that you're seeing, the radio, and all of the blue that you're seeing on X-rays are coming from the same kind of thing, the same reason. And what it is when you have these strong magnetic fields and you have this gas, this plasma that is moving out and interacting and being potentially slowed down by these magnetic fields, it's going to produce a specific type of light. And that's what we're seeing here, except we're seeing it both in the X-rays and the radio waves. And so what is going on here is that all of the plasma is being slowed down a bit by the magnetic fields, and the magnetic fields is stealing that energy and turning it into light and sending it out. But X-rays have a lot more energy than radio waves, right? But on this image, it looks like, you can see all of the X-rays. There's a lot of blue, and you can see a lot of red, even though the radio waves should have a lot less energy. So what's going on there? What's happening is the way that this image was put together. It is taken, so when they take the Chandra image, it's actually a set of a bunch of different pointings. So in this case, it is 11 different pointings where Chandra's looking at each of these fields for a certain period of time. It's, in this case, each time it looked down the field, it's about 5 hours or so per pointing. So the entire region took about almost 60 hours to complete with X-ray observations. And that's remembering that Chandra is up in space. It doesn't have to deal with a lot of noise and background that anything that would be down here on Earth would. The radio, on the other hand, those are telescopes that are here on Earth, and it scanned that entire region, and that took about 25 hours total. And that's a lot messier observations because you got a lot of radio waves bouncing around our atmosphere. So it took a lot longer to get all those X-rays than it did the radio waves. And so that's why they look, similarly bright on this image. But now let's take a look at what's happening over here. So this is where we're starting to see the optical light. This is the kind of light that our eyes can see. And notice that there's not much of it anywhere else. We're not seeing a whole lot of optical light. In fact, most of this region to our own eyes would look invisible. And the reason that it looks yellow is, if you remember your primary colors, if you mix blue with green, that turns into yellow, and that's what we're seeing here. And so what's going on here is, as I said, we're getting a lot of gas that is moving out and is really sending a ton of that material out into the rest of space. But you know what? There's also gas that's kind of sitting out here. And that gas is going to be moving around, not particularly fast. The speed at which all of those gas particles are just bouncing around, that's kind of a little bit, that's basically the temperature of the gas. That's what we refer to as the temperature of the gas. But this thing is moving out super fast because it's been exploded and it's running into this gas. And that gas doesn't have time to tell you, to let people know, the gas beyond it, let people know what's going on. And so we call this a shock. Basically, all of this really fast hot gas is shocking this slower, colder gas that it's running into. It's basically this massive sonic boom in space. And because it's hitting that gas, it's heating it up, and what we're seeing is the glow of the hydrogen going on there. And that's all of that optical light. It's a very thin shell at the rim of this region, and that's what's turning this into, that's the light that we're seeing from this image. So what did all of this? I told you that it's an explosion, but what started the explosion? Well, what we think went on here is we had two stars that died and they left their corpses. They're just basically the leftovers of what happened when stars die. And eventually, these two stars, we think, collided. And in their collision, they created a massive explosion. And so that's what's going on here, but it's not because of the energy from the collision. That's not what's causing the explosion. No, it's something cooler. It is actually, because they're moving so fast, this turns into a big nuclear explosion. So we are using the nuclear energy from the stars interacting with one another, and that's creating this massive, like an atom bomb in space. And these supernova explosions are some of the brightest things that we can see. In fact, we can see them in galaxies that are, close to the edge of the furthest galaxies that, we can see from Earth. And so it's a massive explosion. But we're going to zoom in a little bit to this little shocked region, because it is something that we can see in optical. So these are pictures of that region. We're zoomed in, and this is the original image. So the blue stuff here is that visible light that our eyes can see, taken in 1998. And then we looked again at it with the Hubble Space Telescope, which is kind of zooming around us, back in 2006. And you can see it moved a little. In about 8 years, all of that stuff seemed to move outward a little bit. What that means is that we can try to measure the speed at which it's going. And so it looks like a very small region, but it's actually zooming off really fast. The speed is about 10 million kilometers an hour, or about 6 million miles an hour. Super fast, faster than anything I know. And the amount that it's moved in approximately 8 years is about a light month. So we can go backwards. We can try to say, okay, so we know how fast it's going. We know the rough region of the sky it's in. When did this happen? Well, it turns out that if we do all those back calculations and look in the records, we know that this happened in the year 1006. That's why it's called Supernova 1006, because it happened in that year. And the cool thing about it is that this supernova, because it's one of the ones that's super close to us and really, in our own region, it would have been super bright. And it was super bright. It was recorded in Islamic records and Chinese records and European records. And it was seen for 18 months, over 1,000 years ago. And during its brightest, it could be seen during the day. It was brighter than Venus, which you can also see during the day if you're looking in the right place. So the only things that were brighter than it in the sky were the sun and the moon. It would have looked incredible to see at that point. But the last bit I want to leave you with is there's other effects of this. So scientists have looked into ice cores in Antarctica. So one of the cool things that you can do with ice cores and ice in Antarctica is it records a little bit about what the atmosphere was like back then, right? And all of the gases, that are trapped in the ice. So they've been able to find an effect of this supernova on those ice cores, or what we think is an effect, because this supernova, it's so energetic, it's producing a ton of gamma rays, and those would have hit the Earth's atmosphere and been sealed into the ice. Just a reminder of how much things that are out there, very far away, can potentially affect things here on Earth. So let's take a look at the chat, and there are a couple questions. First of all, no, this isn't an actual color image. One of the things that's really cool that astronomers get to do is look at light that normally our eyes wouldn't be able to see, and they are often telling us something about gas that's at a different temperature, or things that are really cold or really hot, and we can start to put together that image and represent it in colors that we can see. So again, if we go look at the main image, we're talking about gas that is really, really hot. It's so hot that we would never be able to see it with our own eyes. Well, that's it for this episode. Be sure to like, share, and subscribe, especially on YouTube. Feel free to take a look at our previous episode where we took a look at a stunning picture of the Orion Nebula. Also, on YouTube, we have a program called Cosmos from Your Couch. So that's an opportunity for you to get deeper into cutting-edge astronomy that is being done by researchers here at the Dunlap Institute for Astronomy and Astrophysics. Definitely, please feel free to leave a comment and to recommend pictures that you'd like to see us break down in future episodes. And with that, thank you. My name is Mubdi Rahman, and this was A Picture in 1,000 Words.